Hi everyone. In this video we're going to expand upon our knowledge of eigenvalues and eigenvectors and talk about what it means for a matrix to be diagonalizable. And this turns out to have a lot of use in practice. So let's begin with a definition. Let A and B be n by n matrices. So they're both square and they both have the same dimensions. Then A and B are called similar if there is an invertible matrix called V such that, ST means such that, B is equal to V inverse A times V. Yeah? There we go. Okay, or equivalently, we could have that B is equal to VA V inverse. Either's fine. You just swap the roles and this will also give you the same similarity transformation. So, let's see what it means to be similar if two matrices are similar. Turns out this is a really nice property. Let's compute the determinant of B. Well, what's B equal to? It's equal to VA V inverse, isn't it? But now we know that the determinant of the product of matrices is the same as the product of the individual determinants, right? So this is equal to the determinant of V times the determinant of A times the determinant of V inverse. And what's the determinant of V inverse? Well, since V is invertible, we know that it's 1 divided by the determinant of V, which is here. So once the division happens, we're just left with the determinant of A. And that's kind of interesting. So if two matrices are similar, they must have the same determinant. But it gets better. Let's talk about another property of similar matrices. If A and B are similar, then they have the same eigenvalues. And the same algebraic multiplicity. Each eigenvalue has the same algebraic multiplicity. And remember, the algebraic multiplicity is the root of the characteristic polynomial. So really what we want to show here is that the characteristic polynomials of the two matrices A and B have to in fact be the same. What is a characteristic polynomial? I know that the characteristic polynomial of A is the polynomial determinant of A minus lambda I. And remember, our hypothesis here is that there's some invertible matrix V such that A is equal to V, B, V inverse. Well, let's plug that in. Yeah? This is going to be the determinant of VB V inverse minus lambda times the identity. And let's be a little clever here. What's the identity matrix equal to? The identity matrix is the determinant of VB V inverse minus lambda. We're going to write the identity as V times V inverse. And now, from this term here, we're going to factor V, which is common in both, on the left, and V inverse is common. We'll factor that on the right. So inside the determinant, we get that this is equal to the determinant of V times B minus lambda I times V inverse. And make sure you're okay with the fact that both of these are the same. If we redistribute v and v inverse on the left and right respectively, we'll get back to this step. Yeah, make sure that you see this. We can use the same property of determinants that we used in the previous example. We know the determinant of the product is the product of the determinants. The determinants of v and the determinant of the v inverse will divide to give 1, and we're left with just the determinant of b minus lambda I, which is the characteristic polynomial of b. So if the two characteristic polynomials of b are the same, or of a and b are the same, we know that they must have the same roots, and they must have the same algebraic multiplicities of each roots. So our example has been shown. All right. Let's talk. Before we move on to diagonalization, let's finish up a discussion I don't think that we did in the previous video, but let's talk about something. Two eigenvectors from different eigenspaces means that the eigenvalue associated with the eigenspace is different. Two different or distinct eigenspaces are linearly independent. Yeah? Two eigenvalues corresponding to different eigenspaces are linearly independent. So let's see how to prove something like this. Well, we need to start with our eigenvalues and eigenvectors, right? So let's pick an eigenvector for A, right? And our matrix is A. Suppose that AX1 is equal to lambda 1x1. And suppose we have A times another vector x2 is equal to lambda 2 times x2. And what do we know? Because they're both eigenvectors, we know some things. We know that x1 and x2 are not 0 because they're eigenvectors. And we also know that they correspond to differing eigenspaces. So that means that lambda 1 is not equal to lambda 2. Yeah? So how can we go about showing that x1 and x2 have to be linearly independent? Well, let's use the definition of what it means to be linearly independent. Suppose we have a linear combination c1x1 plus c2x2 is 0. And now we want to show that c1 and c2 must both be 0. Yeah? How can we go about doing this? Well, let's suppose that they're not both 0. Yeah, let's suppose that c1 and c2 are not both 0, right? So really we're doing this, it's called a proof by contradiction. We're going to suppose that they're linearly dependent. So c1 and c2 are not 0. Yeah? Suppose they're not 0. What can we do? Let's apply A. Let's multiply A on both sides of this equation. If I multiply A on the left, what's A times C1 x1? It's C1 AX1 plus C2 AX2 equals A times 0 is, of course, 0. And now we can use the fact that these are eigenvectors. And we know that we have, what's AX1? That's lambda 1 x1. So we get C1 lambda 1 x1 plus C2 lambda 2 x2. Ooh, lambda 2. x2 has to also be 0. Yeah? Well, let's make this a little bit easier for ourselves. We know that the eigenvectors, or the eigenvalues rather, are different, right? So at most one of them is 0. So let's make sure, let's pick out the one that's not 0. Let's suppose now, without loss of generality, that lambda 1 is not 0. I know one of them has to be not 0. Let's just call that one lambda 1. Yeah? So what does this mean for us? Well, this means that C1 lambda 1 x1 has to be equal to negative C2 lambda 2 x2, right? And now, because we have lambda 1's not 0, let's multiply both sides of our original equation here by lambda 1. We're going to multiply this equation that I'm pointing to by the non-zero constant lambda 1. So we have that C1 lambda 1 x1 plus C2 lambda 1 x2 is equal to 0 by multiplying this equation by lambda 1. Well, what is C1 lambda 1 x1? I know that that's C2 lambda 2 x2 with a minus sign in front of it. So we get that this is equal to negative C2 lambda 2 x2 plus C2 lambda 1 x2. And I know that that has to be 0. Yeah? And you say, boy, gee, howdy. I have a common factor of a C2, and I have a common factor of an x2. Let's factor them out. So I have that C2 x2 times lambda 1 minus lambda 2 has to be 0. Well, what do I know about C2 now? It's not 0. What do I know about x2? It's not 0, right? So what must we have about lambda 1 minus lambda 2? The difference has to be 0, but that's a contradiction, yeah? So here we have a contradiction. So our original hypothesis must have been false. What was our original hypothesis? That our two constants were not 0. So we must have that C1 and C2 have to both be 0. Yeah? Cool. All right. So let's talk about what it means to be diagonalizable. An n by n matrix is diagonalizable if it is similar to a diagonal matrix. So that means that there's some invertible matrix V such that A is equal to V, D, V inverse. Yeah? And that's not so unreasonable. So what it means to be diagonalizable is that there's a particular similarity transformation, namely you're similar to a diagonal matrix. Yeah? And now what is the diagonal matrix? It turns out that the diagonal matrix D will just be the matrix with the eigenvalues of lambda on its diagonal, with zeros elsewhere. And these are repeated according to their multiplicity, which means that if, like, lambda, let's say we have a 3 by 3 matrix, and we have that lambda 1 is equal to 2 with a multiplicity of 2, and lambda 2 is equal to 5 with a multiplicity, algebraic multiplicity of 5. Yeah? Then what would D be? D would just be the matrix 2, 2, 5. And it turns out the order won't matter for us, and we'll see how to fix that in a second. But you just repeat the eigenvalues according to their multiplicities and put zeros everywhere else. Yeah? And what's going to go in our matrix V? V will be the matrix consisting of a basis of eigenvectors. And this basis is going to be a basis of Rn. Yeah? So we're going to need to demand that Rn will have a basis of eigenvectors. And let's codify that. Theorem. If A is an n by n matrix, this thing is diagonalizable if and only if, so it's both directions, A has n linearly independent eigenvectors. And if we have n linearly independent eigenvectors in Rn, that means that the eigenvectors form a basis. Let's see why this is true. Yeah. Let's let V, again, what's V? It's the matrix with our eigenvectors in linearly independent eigenvectors. So suppose we could find such a collection of eigenvectors of A. Let's throw them in one matrix, call it V. Okay? And let's let D be equal to our diagonal matrix, lambda 1 through lambda n, with zeros elsewhere. And the eigenvalues in the ith column correspond to the eigenvector in the ith column of V. So these line up. Corresponding eigenvalues are in the same spots as their vectors from the corresponding eigenspace. All right, so what are we trying to assert here? We're trying to assert that A is equal to V, D, V inverse. And let's see why this is true. Let us multiply on the right by V. And we get that AV is equal to D times V. Or sorry, V times D. Reading is hard. And let's see that these are actually the same with this assignment. What's the first? Let's look at the ith column of this equation. On both sides, we'll look at the ith column, okay? What's the ith column? It's going to be whenever I take the matrix A and I multiply it by the ith column of V. Yeah? And so what is the ith column going to be for us? That's going to be A times V sub I, right? Well, what's the ith column on this side of the equation? It's going to be the matrix V times the ith column of this diagonal matrix. But what happens whenever I multiply the matrix V by the ith column of this diagonal matrix? Well, what's the entry in the ith column? It's just lambda I, right? And zeros fill the entire column. So the only vector that I'll really be multiplying for in V is VI. Yeah? And so really what this expression AV equals VD is just a matrix form of all of the eigenvalue equations, eigenvector equations. And the diagonalization, similarity transformation, just solves for A in this AV equals VD. Yeah? Cool. Let's recall now that 1 is always less than or equal to the geometric multiplicity, and that's always less than or equal to the algebraic multiplicity of any eigenvalue. And let's recall again just the words. The geometric multiplicity is the dimension of the eigenspace corresponding to lambda, and the algebraic multiplicity is the multiplicity of the root, multiplicity of lambda as a root of the characteristic polynomial. Yeah? And so let's talk about a little theorem. If A is n by n, and A has n distinct eigenvalues. A has n distinct eigenvalues. What does it mean to have n distinct eigenvalues? That means that each of their algebraic multiplicity is 1. Well, what does that mean about the geometric multiplicity? The geometric multiplicity is at most 1, And if they're indistinct eigenvalues, then we must have that their algebraic multiplicity, the geometric multiplicity is at most 1. So that means that the dimension of the eigenspace corresponding to lambda, the geometric multiplicity, is 1. Yeah? Well, if we have that the dimension is 1, what does that mean about the eigenvector? So that means that the eigenvector corresponding to lambda forms a basis for its eigenspace. Yeah? And what else can we get from this? If we have indistinct eigenvalues, and we will have distinct eigenspaces, right? What do we know about eigenvectors from distinct eigenspaces? They must be linearly independent. So that means that the eigenvectors will form, how many eigenvectors will there be? There will be n of them, because they have to sum up, the sum of the algebraic multiplicities has to be n, right? Because that's the degree of the characteristic polynomial. So the eigenvectors will form a basis of Rn. So if we have indistinct eigenvalues, then we know that we have a basis of eigenvectors. And let's just be clear, when will we always have a basis of eigenvectors? We will always have a basis of eigenvectors whenever the sum of the dimensions of the eigenspaces is equal to n. Yeah? We want the sum of the eigenspace, the dimensions of the eigenspaces to be n, and this is the condition where we'll always have a basis of eigenvectors. And we have it here because we have indistinct eigenvalues. Each eigenspace has dimension 1. What happens if you sum all of these? You get n, right? All right. Let's do an example together. Determine whether the following matrix is diagonalizable. Let A be our favorite matrix: 2, negative 2, negative 2, 3, negative 3, negative 2, 2, negative 2, negative 2. Yeah? Pause the video, see if you can figure this out for yourself.